Okay, hello again, everyone. I think it's time to resume now. So, as I said, we'll have two last but not least talks in this session. So, our first presentation will be given by Tim Yammer from TU Darmstadt. And the presentation will be entitled "A Comparison of the Scalability of OpenMP Implementations." Let's go.
Hi, my name is Tim Yammer and welcome to my presentation about the scalability of different OpenMP implementations. So I think you might be familiar with OpenMP to some degree, as it is one of the most commonly used ways to achieve parallelism inside one node. Newer systems offer much higher degrees of parallelism, but not only in terms of the number of nodes, also they often provide more and more cores per node, therefore utilizing the parallelism inside a single node as efficiently as possible is a critical component in order to achieve maximum performance. And in previous work, we discovered that there are some scalability issues with OpenMP runtimes, but we did not investigate the reasons for the scalability differences of different implementations so far. So in this talk, we want to analyze the impact of different implementation choices made and the system architecture on the scalability of the different implementations. We are curious if the previously detected scalability problems are still relevant today. And maybe we could learn something from the different implementation approaches that are taken by different implementations of the OpenMP standard. And also we are curious if we can see the impact of the system architecture. Because modern CPUs are available that do not offer a core count that is an exact power of 2 anymore. For example, you can buy CPUs that have 6 or 12 cores available. And as you can see in this picture, this might lead to a somewhat asymmetric internal CPU structure. And we are curious if we can see the impact of this internal structure on the scalability of OpenMP. So the outline of this presentation is quite straightforward. I briefly want to introduce you to our experimental setup and then talk through a selected list of OpenMP constructs. For the full list of constructs that we've analyzed in our study, please refer to our paper. So we conducted our experiments on the Lichtenberg high-performance computer here at the TU Darmstadt, and actually we used the old Lichtenberg system, not the new one that have entered the top 500 at place 93 on this ISC. As we want to have access to the source code because we want to compare the different implementation choices made, we will compare the most commonly used open source implementation of the OpenMP standard, that is the GNU implementation that is used in the GCC compilers, and the Clang and the LLVM implementation that is used in the Clang compilers. We will use the system default version at the time of our study. Of course, we need to take care about thread placement, and we'll use the OpenMP provided environment variables to do this. And the only thing that we need to do to our data before we can show it to you is that we cut the top 10% of our measured timings. This is because we want to filter out the noise when the operating system interrupts the process for some reason. So let's get right into it and talk about the performance of the different implementations of OpenMP. Here you see at the x-axis the number of threads, and the y-axis depicts the overhead. And the overhead in this case for the single clause is the time that the threads that do not actually process the single region, these threads spend within the single region. So what we do is we take a timestamp, and then comes the single region, and then another timestamp. And basically between those two timestamps, the time should be basically 0, so as low as possible, at least for the threads that just skip the single region, as we have specified in no wait clause, and there is no implicit barrier. So if you compare the left-hand figure to the right-hand figure, you see that on the left side we utilize a closed thread binding, and on the right side we utilize a spread thread binding. But the general trend behind these two figures is the same. So you see that for the GNU implementation, the overhead rises quite linearly in this case, while the overhead for the LLVM implementation stays roughly the same. And this is the same for the closed thread binding. But if you look very closely, here you can see a 12 or 18 thread, there is a rise in the overhead for the GNU implementation. And this is because our system is organized into 4 NUMA nodes with 6 cores each. So if the next thread is placed on the next NUMA node at 12 or at 18 threads, then you can see the impact of this. This is why we will utilize the closed thread binding for the rest of this presentation. So here we see that for the GNU implementation, the overhead rises, while it stays roughly the same for the LLVM implementation. And the key thing is, of course, why is this the case? So is the LLVM implementation really superior to the GNU implementation? So let's have a look into the source code. The general idea behind these two implementations is the same. So you have a single counter that counts the number of single regions encountered so far, and each thread has its local counter, and it is incremented whenever a single region is encountered. And then there is a team's single counter. And so this compare and swap operation tries to increment the team's shared counter. So the first thread that arrives at this code block will increment its local counter and then increments the shared team counter. And the second thread that arrives will increment its local counter and then cannot increment the shared team counter as it has been incremented by another thread so far. So the first thread that arrives will increment the counter and then process the single region, and the other will fail to increment that counter and will then skip the single region. And this is also the idea that is behind the LLVM implementation. So you have a thread local counter that counts the number of single regions encountered. It will be incremented the same as for the GNU implementation. And then you spot the difference here. First, there is a non-atomic compare operation. And then you have the atomic operation, which is the same as for the GNU implementation. The team's counter should be incremented. So there is an addition of this non-atomic compare operation. What happens in the LLVM implementation is that not every thread issues an atomic operation. Only if it spots an opportunity to increment that counter, only then an atomic operation is needed. Otherwise, it will just skip the atomic operation. And this will lead to less congestion. And this is the reason why there is with more and more threads, there is more and more congestion in the GNU implementation, but this is not the case for the LLVM implementation, because this non-atomic compare operation does not create congestion. So in this case, we could learn from the from the LLVM implementation that we could use less atomic operation. And in this particular case, the addition of this one non-atomic compare operation does not hurt performance. Yeah, actually, it is beneficial to performance, as you've seen. So let's have another look at the barrier implementation. Here you see again the number of threads versus the overhead. The overhead in this case is the time between the last thread arriving at the barrier and the last thread leaving the barrier, because this is the time that at least one thread spends processing the barrier operation, although this is not needed by the semantics of the barrier operation. Because once the final last thread has arrived at the barrier operation, then all threads should resume to the user code as fast as possible. Here between the left hand and the right hand figure, the distinction is in the order that the threads enter the barrier. So on the right hand side we have a synchronized thread order, which means that all threads arrive at the barrier at roughly the same time point. In contrast, on the left hand side we see a random thread ordering. This means that each thread has that we have a time frame, and each thread uniformly at random picks a time point within this time frame and enters the barrier at that time point. So there is a small delay between the thread entering. And we can have a look that the GNU implementation's overhead rises quite linearly, so I suspect there might be a linear scheme behind that. And you see that the LLVM implementation's overhead has a logarithmic curve, so I suspect there might be a logarithmic scheme behind that. So let's have a look at the scheme behind that, and indeed LLVM utilizes a tree-like scheme while GNU utilizes a single shared counter. But apparently the GNU implementation, as you can see, the GNU implementation works very well if there is a small delay between the threads arriving at the barrier. So imagine that thread 0 is the last thread arriving at the barrier. The only thing that thread 0 has to do in this case is it has to increment the counter by 1, and then all threads can proceed with the section after the barrier. In contrast, in the LLVM implementation, what the final thread that arrives at the barrier has to do, it has to process the whole tree in order to gather that all other threads have also arrived at the barrier. And therefore, the work done by threads 1, 2, and 3 in this case, they can be somewhat shadowed by the application's load imbalance. As the thread 1, 2, and 3 in this example has to wait for thread 0 to arrive anyway, they could do some of the work needed in order to gather that all threads already have reached the barrier. So in this case, we could learn from the GNU implementation that some of the overhead needed in order to perform this barrier operation, some of these overhead can be shadowed by the application's load imbalance. The thread have to wait for the final thread to arrive anyway, so they can do some of the work that is needed in order to perform the barrier operation. But we could also learn from the LLVM implementation that a logarithmic scheme works better with a higher number of threads. Of course, the overhead only grows logarithmically in terms of the number of threads, and with more and more threads, this shadowing of the overhead in GNU is not sufficient anymore. So at some point, the application's induced load imbalance is not enough in order to shadow the higher overhead that is needed in order to perform this linear scheme. So in this case, there is no single implementation superior in all cases. Let's have another look at the reduction operation. Again, you see the number of threads versus the time needed to perform the reduction operation. And as you can see, you have this linear rise of the overhead in the GNU implementation, and there is a logarithmic curve in the LLVM implementation. And if you then look into the source code, this is indeed what happens. GNU utilizes a linear scheme, meaning that each thread writes its value to an array, and then the master performs the reduction of this join barrier. And in the LLVM implementation, the reduction is organized in such a way in accordance to the join barrier, which is a tree scheme. So one thing that we note is, here we plotted the cache misses of the reduction operation. And we note that the GNU implementation does not have a lot of cache misses. Basically, first, each thread writes their local value into an array, and then there are some cache misses when the master thread collects the results. In contrast, the LLVM implementation, the tree scheme, have a lot of cache misses. But what we see, and what's very interesting, is if you look at 12 or 18 threads, then there is no steep rise in cache misses, as one might expect. And because we utilize one additional NUMA node, but this does not increase the number of cache misses. So we do not see that the structure of the reduction operation is aligned with our system structure, for example, with the different NUMA nodes. And this is not the case. One particularly interesting thing to note is that if we stay inside a single NUMA node, the very simple approach of the GNU implementation is very performant. Here you see that at 4 thread, for example, you need to introduce another tree layer if you want to have the 5th thread. The LLVM implementation needs to introduce a tree layer, and this is not needed in the GNU implementation. So in this case, we could learn from the GNU implementation that this linear approach has less overhead for a low number of threads. It might even be possible to vectorize the reduction operation in these cases. In contrast, it is not possible to vectorize a logarithmic scheme, a tree scheme. But this logarithmic scheme works better with a higher amount of threads, of course. So here it might be a good idea in order to combine these two implementations, where, for example, first GNU-like linear approach is used in order to reduce the values inside a single NUMA node, and then we utilize a tree scheme in order to combine the values from the different NUMA node. So in summary, there is no implementation that works best in all cases. In general, you could say that the LLVM often utilizes logarithmic approaches, and this works better with higher thread counts. But the GNU implementation often utilizes a simpler linear approach, but this works better with lower thread counts as there is less overhead introduced in some cases. Previous work already suggested the usage of so-called adaptive implementation, which means that an implementation might be able to adapt in regards to the number of threads. For example, we want to utilize a GNU-like linear scheme and then switch to an LLVM-like logarithmic scheme once a sufficient number of threads is used. Also, it might be beneficial to adapt in regards to the system layout, for example, first reducing the values inside a single NUMA node and then reducing the values between the NUMA node. But we did not find such a behavior in our study, so therefore we think that there is still room for improvement in this area. And with this, I want to thank you for your attention.
Hey, team, are you there? Yeah, I can see you. Hi. Okay, awesome. Thanks a lot for your presentation, team. So as I said in the Slack channel, the most reviewers enjoyed the work and most comments were related to figure improvements and typos. So there were not that much questions. There was one, however, regarding, as you're saying, that there is no clear winner in all this, and whether it would make sense to, whether it would be possible to give like general advices on how to choose one. I'm not sure whether it makes sense, but can you
Yeah, I've tried a
What's
bit
your
to
take on
highlight
that?
it in the
If you had to pick a...
presentation. Of course, there is
Mhm.
like no clear winner, so to speak. And in some cases, the GNU implementation works better because the linear scheme has less overhead for low number of threads. But if you then utilize more and more threads, then often the LLVM implementation is the winner here. So I think this would be the general advice that you can give.
Okay. I'm not sure I've fully understood what your conclusion was regarding adaptive scheme, because you said some people have been proposing to use adaptive schemes, but which makes sense because, as you said, in some cases you want to use one approach, in other cases you want to use the other one. And then you say, but we never saw that or in our experiments, so I'm not sure I followed you there.
Yeah,
If
so
one approach is better than the other, couldn't you just try one or the other online and based on that, pick one automatically?
yeah, exactly. So this is one that might be beneficial, but so far we did not see such an approach in the implementation that we've analyzed. Yeah, and especially
Okay.
regarding the other question about the other system architecture. Yeah, and this would also be a very interesting thing to look into because the system architecture is not taken into regards in any way, and therefore it's very interesting to try out to react to different system architectures. Yeah, but the conclusion there is that we did not find such a behavior.
Okay, thanks. We have a question from Hatem Heltayef. Thanks for the talk. Are you planning to look at the overhead of tasking programming models?
Yeah, we also included it in our paper, but not in the presentation as it would take too much time.
Okay. Maybe you can say a few words about this for those who haven't had the opportunity to read your article yet.
So in general, the idea is that there are also differences in the implementations, and what the LLVM implementation does, it has multiple tasking queues, and if you have multiple threads that spawn new tasks, this is beneficial as long as there is not too much load imbalance and too much stealing of the task occurs. And in contrast, you have only one task queue in the GNU implementation. The GNU implementation only maintains one queue where the tasks are stored, and this might lead to a lot of congestion if there is a lot of short tasks involved.
Okay, thanks a lot. It's pretty clear, I think. I can see that some people are writing stuff on the channel, so let's wait for this to show up. I see Mache and Tomaropa writing something. Okay, so then let me read the question from Mache. I've noticed that you did your test on a Haswell-based CPU. Do the results still stand in case of newer offerings from CPU vendors? I think that in Skylake Intel significantly improved the communication path between NUMA nodes.
Yeah, so we've not tried CPUs from other vendors so far, but it would be very interesting to do so, of course. And the main thing here, what we try to emphasize is that we have done a comparison between the LLVM and the GNU implementation, and the point that, for example, there is some shadowing of the overhead for the barrier for the GNU implementation. This will still hold true for other CPUs as well.
Okay, and we have a last question from Thomas Ropard. Did you look also at the notion of fairness in this case it could make sense?
No, in our overhead decision, we've not taken fairness into account.
Okay.
Sí, mami, yo había preguntado hace un tiempo y valía muy cara, valía como 250,000 pesos, pero en un lugar,
I
pero
think
yo había visto en
someone
otra
left his
parte.
mic up.
Voy a preguntar en esa otra parte a ver cuánto valen.
I'm not sure I can read. Elvis, I think your mic was open. Okay. Okay. So I think we're done. If there are other questions, feel free to ask them on the channel. I'm sure Tim will be happy to answer them. Thanks a lot again.
Yeah, thank you
Tim,
for your questions.
For your very clear presentation. Let's move to the last presentation of this conference. So it will be given by Andrei Poenaro from University of Bristol. And so last talk will be on the evaluating the effectiveness of a vector length agnostic. Oh, wait, what happened? Zoom. Sorry, evaluating the effectiveness of a vector length agnostic instruction set.
Hello, my name is Andrei Poenaro. I'm a PhD student with the HPC group at Bristol in the UK, and today I'm going to present to you a summary of our paper evaluating the effectiveness of a vector length agnostic instruction set, which looks at modern vector computation with a focus on ARM SVE. My work is around modern and future architectures for HPC, and at Bristol we have experience with most of the common HPC architectures in use today, including ARM-based CPUs such as the Marvell ThunderX2 and the Fujitsu A64FX, x86-based CPUs from Intel and AMD, and GPUs from the three major vendors. We study architectures from two perspectives. We look at differences between platforms and how to obtain the best performance on a wide range of them, and we do focus studies to understand the depths of individual architectures. One of the architectures we are currently most interested in is the Scalable Vector Extension, or SVE, from ARM. SVE is a relevant architecture to study because of its use in the newest generations of ARM-based HPC processors. Fugaku, the #1 supercomputer in the top 500, uses Fujitsu A64 processors which implement SVE, and in our own Isambard 2 we hope to add some of the same processors later this year. At Bristol, we've been studying SVE since it was announced a few years ago. We think it's very important to get an early start, not only to be better prepared when the hardware arrives, but also because early experiments help improve toolchain maturity. Using emulators and simulators, we have worked directly with ARM and a number of supercomputer vendors to identify and fix many pre-release issues, which has led to stable and performant toolchains from the very first released versions. SVE also prevents a novel research problem. Because vector length isn't fixed, but rather each implementation can choose its own, it is important to understand the impacts of this choice on application performance. To study SVE, we took a collection of mini apps that we've worked a lot with in the past. These are mini apps that we understand very well, both in terms of the code and their performance profiles, and each of them is representative of a wider class of HPC applications. Stream is the de facto memory bandwidth benchmark. BUDE is a compute-bound computational chemistry mini app. T-Leaf and Cloverleaf are structured grid applications. Neutral is a Monte Carlo particle transport application. MiniFMM is a task-based mini app that implements the fast multipole method. And Megasweep is a benchmark we developed based on the kernel of the Snap proxy app for deterministic particle transport. We're interested in the vectorization characteristics of these applications, so we ran them on a single thread, a single MPI process where applicable, with all the I/O, initialization, and finalization stages removed, such that we only capture data about the core kernel. We used a combination of static and dynamic analysis tools, and the ARM instruction emulator, or ARMI, was the main tool we used for instrumentation. ARMI allows you to run SVE applications on regular ARM v8 hardware, but it also lets you add custom instrumentation to record data about how your application performs. You can also simulate SVE applications. The Gem5 simulator, for example, has an SVE version, but because these are orders of magnitude slower than real time, it makes it harder to evaluate real-world problems. The first step in our analysis was to investigate how the application is vectorized, both on SVE and on the other current generation vector platforms. We selected the main computation loops from the applications and looked at the compiler's ability to vectorize them in the three main HPC compilers, GCC, Cray, and ARM and Intel on the respective platforms. Each of the applications is presented as a row in this table. Immediately to the right, we list the number of core loops analyzed and their percentage of runtime on a real core of ThunderX2. Then, the compiler's performance, in terms of number of loops vectorized, is clustered by platforms. First is SVE, then Neon, the previous generation vector instruction set from ARM, and the one that ThunderX2 uses, then AVX. The results were the same for both AVX2 and AVX512, so they are shown as a single cluster in this table. Each cell is color-coded according to the percentage of loops vectorized. While the Intel compiler vectorized the highest number of loops on x86 platforms, the compilers which can run on all the platforms studied, GCC and Cray, vectorized at least as many loops on SVE as they did on Neon and AVX, and sometimes even more. This supports SVE as an instruction set that is well suited for scientific compute. Please note that the Cray results are obtained from a pre-release version of the Cray compiler for SVE. We then took each application and looked at the dynamic count of instructions executed using custom instrumentation through the ARM instruction emulator. This graph shows the instruction usage data for BUDE, the molecular dynamics mini-app. The leftmost cluster shows the data for a run in which vectorization is explicitly disabled. The next one shows data for a neon target, such as the Thunder X2, and the remaining clusters each correspond to a selected SVE vector width, which can be given as a parameter to the emulator. Within each cluster, the colors correspond to different types of instructions. The light green is scalar ARMv8 operations, the orange is neon, and the other colors are all different classes of SVE instructions. BUDE is a compute-bound application which makes good use of vectorization, so the number of executed instructions decreased as the vector length was increased, because each single instruction processed increasingly more data. Cloverleaf, the fluid dynamics mini-app, showed a different profile. First, not all of the code is vector code, so a significant portion of scalar instructions are executed even at wide SVE lengths. Most of the scalar code is from outer loops in loop nests, because the compiler only vectorized the innermost loops. Second, while all three compilers showed similar behavior at narrow widths, the number of instructions executed by the version compiled with Cray decreased much faster with vector length, suggesting better vectorization. With the Cray compiler, the number of scalar instructions also decreased with vector length, which may seem counterintuitive but can be explained by looking at how these compilers vectorize loops. ARM and GCC generate vector length agnostic code that can run on any vector width, but with Cray, the width needs to be set at compile time. With this information available, the Cray compiler generated scalar instructions for most of the loop control flow as opposed to SVE instructions. But the number of times these were executed still depended on how much data each vector instruction processed, thus resulting in a correlation of scalar instruction count with SVE width. For most of the mini-apps, regardless of what percentage of runtime was spent in vector code, when vector instructions were executed, the vector registers were fully filled. But in SVE, each instruction is predicated per lane, so it is possible to run vector instructions where any number of elements are masked out. In the worst case, this can mean executing vector instructions that only process a single useful element, thus gaining no benefit from this suboptimal vectorization over scalar code. We observed this effect to various extents in mini-FMM. Looking at the dynamic instruction count for mini-FMM provided a first hint at the issue. Vectorization does decrease the total instruction count up to 512 bits, but using larger vectors brings little benefit. Vector code is still being run at all lengths, but the number of instructions was very similar at 1024 and 2048 bits compared to 512 bits. This happened because even though wider registers were available, they were not being filled with useful data, and many of the lanes were masked out. This graph shows a histogram of the number of bits active in vector operations, grouped in 128 white bins. A higher bar means more accesses had a number of bits active that falls in that bin. In each column, the last bar shows the percentage of operation in which all the lanes were active. When the vector registers are 128 bits wide, for example, the only way for an access to have between 128 and 255 bits active is for it to have exactly 128 bits active. Data is not shown for the Cray compiler because mini-FMM's build system does not support Cray. We can see that up to 512 bits, most of the accesses use the full vector width available. However, at 512 bits, already only a little over half the accesses use the full width, as opposed to more than 80% at the 128 bits. Going up to 1024 bits, some operations use more than 512 bits, but very few utilize the full 1024 available. At 2048 bits, the histogram is virtually identical to the 1024 one because the additional vector width is not utilized. This mini-FMM example highlights that with SVE, because of the per-lane predication, it is not enough to check that vector instructions are being run when analyzing performance, because it is possible for those operations to only use a small portion of the throughput available. Finally, in our paper we looked at how SVE was used for memory accesses. One of the new features in SVE compared to Neon is non-contiguous memory accesses in the form of gather loads and scatter stores. Of the applications we studied, Cloverleaf and mini-FMM use such non-contiguous accesses. This slide shows Sankey diagrams for the types of memory accesses performed by these two applications. Within each diagram, the widths of the bars are proportional and they all add up to 100% in the total bar on the left. For both applications, most of the memory operations were loads, about a third of which were SVE operations. The main difference is that Cloverleaf only performed a small percentage of non-contiguous accesses, and all the lanes were active the vast majority of the time. In Mini-FMM, however, about 8% of all memory accesses were gathers, and in about 15% of all accesses, only a subset of the lanes were used. Mini-FMM's usage of non-contiguous operations and partially filled vectors was not a performance bug. Instead, this highlights the flexibility of SVE. Due to the nature of the task-based FMM algorithm, a lot of the operations don't benefit from wide vectors, and the ability to mask out lanes enables it to use at least some of the vector power. In a fixed-width scenario without predication, many of these operations would have been run scalarly instead. With A64FX processors becoming available this year, we will soon be able to analyze SVE performance in a real hardware implementation. In the meantime, we have continued our work on simulated SVE, and we will present a paper studying the effects on cache of wide vectors using a subset of the same mini-apps shown today, at the EAHPC workshop as part of Cluster 2020. This paper not only looks at interactions between wide vectors and different cache configurations, but also investigates the access patterns in non-contiguous memory operations. We gathered all the data for the cache paper using an in-house simulator, but we are building a project that aims to be much more than that, a flexible, accurate, and fast simulation toolkit for HPC architectures. We call this project SimEng, and its first goal is microarchitecture design space exploration centered around SVE, with further extensions planned to support the other common HPC architectures. With that, I thank you for watching, and I encourage you to visit our GitHub pages, where you'll find reproducibility data for this paper, our up-to-date benchmarking scripts and results, and details about our other current work.
Okay, thanks a lot, Sandrei. Are you there? Yes, you are.
I am. Hello.
Thanks a lot. So, lucky guy, you won't have any question regarding reproducibility. You already made the job. So there was a question by Hatem Altayef, who says, thanks for the talk. Can you explain why there is no difference in vectorization, why no difference in vectorization is observed between AVX2 and AVX512 on your benchmark for single core execution?
So I assume that question is in regard to the table that was showed at the beginning of the talk. That was only static analysis data about the applications. So those numbers were extracted by compiling all the applications and looking at each of the loops in the kernels individually and counting how many of those were successfully vectorized by the compiler. There was no difference between AVX2 and 512 because AVX 512 is already more flexible than AVX2. So if it was already able to vectorize with AVX2, it could do as well with 512.
Okay, thanks. Waiting maybe for others to ask questions. I see people typing text. Several reviewers are at concern or questions about the accuracy of the simulator on existing hardware. So are there studies from Fujitsu, Marvell providing feedback on future hardware? And more fundamentally, the question was how to differentiate between the quality of the emulator, the ones the compilers, and the gains of SVE.
Okay, so I think this question has two sides. One of them is about the accuracy of the tools used in this study. For this data, I've used the ARM emulator, which is not a simulator. It doesn't show any kind of performance data. There is no concept of timing in it. It runs all the ARM instructions on the host, and then when it encounters SVE instructions, it emulates them. So the functional result is the same, but it does not simulate any of the architectural components in a processor that would implement SVE, which is why there is no reference to time and a quantifiable metric of performance. The second part of the question, how can you distinguish between the quality of the tools and the programs that they're simulating is a very important one. With SimEng, the simulator that we're building, we're validating this against many different benchmarks that are commonly run. Many apps that we understand very well, like those I've shown in this talk, for example. And once you have a foundation, once you're certain well, fairly confident that your tool is accurate, then you can use it for novel experiments. As far as we're aware, there aren't any widely available tools that can show this kind of performance data on upcoming SVE processors. And this is one of the motivating reasons for building SimEng, because a flexible simulator that lets you clearly define what your system is and obtain simulated performance data is something that will be useful in today's HPC research environment.
Thanks a lot. We have another question from Hatem Al-Tayef, who thanks you for your answers to his previous question. So did you have the opportunity, since you submitted this work, to validate your research outcomes on the Fugaku nodes?
No. Well, we have been doing work with some A64FX hardware, but I don't have any results I can share as of yet.
Okay, thanks. Another question from Maciej Pawelk. Great work. I wonder, is it possible to improve the utilization of wide, larger than 512 bits registers in presented codes? Do you think using wider operations will be required to utilize the full performance of the SV2 equipped CPUs?
For the first part of the question, yes, I think there's definitely an opportunity to improve performance. All the experiments that we've done so far were based on compilers that only support a generic SVE model, because SVE hardware was not available until A64FX. And actually, I think GCC and LLVM still don't have A64 as a target. They can't generate code that's optimized for these SVE platforms. So certainly there is potential for the compilers to generate more optimal code once they understand these platforms better and can tune their output for them. As for using wider vectors to achieve performance in SV2, I'm not aware of any SV2 microarchitecture that's been announced. So depending on what that looks like, it may be that we need to use wider vectors, it may not be. There's also the question of how many of the applications that are used in HPC are ready to support wide vectors, because up until now, 512 has been the widest vector width we've seen. And as I showed in one of the slides, some applications already have trouble going beyond that. So it may not just be a question of, is the hardware able to do wider vectors, but does the application naturally map onto these wider vectors, which is an open question, I think.
Okay, thanks a lot. Somehow it answers some of the other questions I had in mind. Do we have any more questions? Cannot see anyone typing. Well, if not, I think we're almost on time. Well, we are on time. So, well, thanks a lot, Andre, for your presentation or your very clear answers to all the questions that people had. Thanks. Let's thank again all the speakers for, well, the hard work. This is a difficult exercise, presenting your own work remotely and trying to answer questions on the fly like that. Without real feedback from people. So thanks again, everyone. And let's hope we'll meet for real anytime soon and have coffee together for real as well. See you soon. And yeah, see you. Thanks. As Maciej is saying, after this session, you should please join room A for the closing session. So hopefully we shouldn't be too late. See you soon.